Welcome back, folks. We are doing the last part of section 10.3, and we'll be focusing on something called the fundamental identities, fundamental trig identities. As I mentioned in class, these aren't included in any of the WebAssign problem sets, and that's because they're the types of problems that we'll be doing don't really lend themselves to that type of format of a homework assignment. This stuff really has to be written out, can't be done in a computer with all those math entry boxes, etc. We'll start real quick here just to review some things from the past, or that maybe you remember from a previous trig course, and then we'll talk about new stuff. First identity we're going to use is cosine squared plus sine squared equals 1. And that works for any angle theta, positive, negative, greater than 2 pi, less than 0, etc. Why does that work? Well, and why is it called the Pythagorean identity? Because we can create a little right triangle in our unit circle with a hypotenuse of 1. That's the radius of 1. That's why we call it the unit circle. And hopefully you recall that cosine theta is the length of that side there, and sine theta is the length of that side there. The coordinates of this point are cosine theta comma sine theta. That's where we get those lengths from. And the right triangle Pythagorean theorem says that leg squared plus leg squared equals 1. That's why cosine squared theta plus sine squared theta equals 1. Okay, that's great. Now this one, 1 plus tan squared theta equals secant squared theta, that's a little new. That was in the previous video. We talked about, I kind of derived this for you. I'll review it here very quickly. This length right here is 1. Why? Because the unit circle has a radius of 1. This length here is tan of theta. That length is the tangent of theta. And then the hypotenuse has a length of secant of theta. So again, the Pythagorean theorem holds. I have leg squared plus leg squared equals hypotenuse squared. The only other one that I'll mention is 1 plus cotangent squared equals cosecant squared. Hopefully that is similar enough to the previous one that you can figure that one out. I'm not going to show you the geometric interpretation of that. I just don't think it's necessary. All right, so three big ideas here I want to talk to you about before we get into some strategies and some actual example problems. Here's the first big idea. Trig identities are like a puzzle, so this should be really fun. I don't know about you, but I'm pretty excited about this. It's really like kind of putting a puzzle together to figure out how to get from the start of the problem to the end. Number 2, you won't be solving anything. You'll be verifying stuff, and that may sound kind of unsatisfying to you, but trust me, it's going to be really exciting. What are the 3 most dreaded words in math class? Folks, what are they? Go ahead, why don't you turn to your shoulder partner and see if you guys can come up with a guess for what the 3 most dreaded words in math class are. You got them? Okay, here they are. Show your work. 3 most dreaded words in math class, and unfortunately for you, that's really all there is to these problems, is showing your work. There's no final answer, there's no number answer. You have to show work to get from point A to point B, and I'm going to tell you now, or I'm going to provide you some strategies to do that. These strategies for verifying identities, these are from your textbook, and they're covered on pages 745 to 752. I'm going to go through these quickly, and I will give you some additional things that you can use throughout these problems. First bullet point there says try working on the more complicated side of the identity. So we'll take the side that's more complicated, and we'll do all our work there. The other side will remain untouched. Okay, so we won't do anything to the other side. So I'll make that note here. Leave, we'll say the less complicated or the easy side untouched. Okay, next bullet point. Use the reciprocal and quotient identities in Theorem 10.6 to write functions on one side of the identity in terms of the functions on the other side of the identity. Simplify resulting complex fractions. So what are the reciprocal and the quotient identities? These are ones that we have introduced recently. We know that tan theta is equal to sine theta over cosine theta. We know that the cotangent of theta is cosine theta over sine theta. We've got two others. Secant theta is 1 over cosine theta. Last but not least, cosecant theta equals 1 over sine theta. Folks, just a quick sidebar here. You'll notice sometimes I write this, and sometimes I write this. Which is correct, and which is better? They're really both correct. They both mean the same thing. This one is the more mathematically correct one, though. It's you have a function sine, and theta is your input to the function. So this is the more correct way to write it. Sometimes I choose to write it this way just to consolidate space and consolidate characters. Okay, moving on. The next bullet point here says add rational expressions with unlike denominators by obtaining a common denominator. So if we're adding two fractions, make sure we have a common denominator. Next one says, bullet point says, use Pythagorean identities in Theorem 10.8 to exchange sines and cosines, and then you can read the rest of that on your own. The Pythagorean identities we talked about at the top of the page. Next bullet point, multiply numerator and denominator by Pythagorean conjugates in order to take advantage of the Pythagorean identities. So we have talked about conjugates before. Any binomial has a conjugate. So a binomial is something like it's any two terms, something like a plus b. That is a binomial. Its conjugate is you just flip the sign in between them. So the conjugate of a plus b is just a minus b. And when we were working on difference quotients earlier in the year, we used conjugates to help us get rid of some radical expressions. And I'll just show you real quickly what the conjugates we're going to use are to help us kind of get back to those Pythagorean trig identities. Let's say I have the 1 minus cosine theta. Let's say I have that term. Its conjugate is 1 plus cosine theta. And what do I get if I do the product of those two? I'll have 1 times 1, and I'm going to FOIL this out. I'm going to have 1, and then I'm going to have minus cosine theta. And I'm going to have, let's see, plus cosine theta. Some of you can do this really quick, and that's great. I'm going through this one slowly just so that everybody can see where each of these terms come from. The last terms in foiling will be cosine squared theta. I have negative cosine times cosine, so that's minus cosine squared. This bad boy simplifies to 1 minus cosine squared of theta, and that really equals sine squared theta. If you go back and look at our Pythagorean identity, sine squared plus cosine squared equals 1, we can rearrange that to get 1 minus cosine squared equals sine squared theta. We can do the same thing with 1 minus sine theta. Its conjugate is 1 plus sine theta. And we're going to get something similar. We're going to get 1 minus sine squared theta, and that's going to equal cosine squared theta. Folks, there are more of these conjugate pairs, and I'm going to just point you to page 751 of the text. if you want to take a look at some more. But those two with sine and cosine are the ones that we'll use most often. Okay, now we have the last bullet point here. It says if you find yourself stuck with one side of the identity, try starting with the other side. Okay, enough talking. Let's actually do an example. So here's our example. It says verify the identity below. Tan theta equals sine theta times secant theta. So I mentioned earlier that there's no solving going on. We're just verifying that this statement is true. And we're going to pick one side of this equation to work on. And the suggestion was to try working on the more complicated side. So to me, the more complicated side looks like sine theta times secant theta. So what I'm going to do is I'm going to work on that with what I know about trig and algebra and try to make it look like tan theta. Let's see what we can do here. So I got sine theta times secant theta. Well, secant theta is 1 over cosine theta. And sine theta is the same as sine theta over 1. If I multiply those two fractions, I'm going to get sine theta times 1 over 1 times cosine theta. And sine theta divided by cosine theta is tan theta. So at this point, we're done. We have verified that identity because we have an expression here that is exactly the same as what we had here. Again, I didn't touch the left-hand side of this equation. I left it alone. I worked on the more complicated side until I produced what was on the left-hand side to begin with. Okay, folks, part 2 of this video, we'll do the rest of the examples on the back side of your notes page.